Hello, everyone. My name is Jawad Shukri, and I'm one of the organizers of GeoHackathon 2024. We are delighted to have Tim Lines here today to speak about Geothermal Field Development Plan. Tim Lines is the co-founder of Texas Durham Geothermal, the developer Geothermal Wells, and geothermal advisor with US Project InnerSpace, in which he is the admin of finance facet of the $160 million US dollars for a project in Department of Energy. The project name is Geothermal Energy from Oil and Gas Demonstrated Engineering. He is also a former energy policy advisor to the European Commission's Central and Eastern European FAIR program, which included his leading of drafting the district heat legislation and also regulating for 13 Central and Eastern European countries, and Romania's alignment with the energy chapter of the AKI community. He also he has worked in the energy sector for 40 years and also served on the boards of 3 oil and gas companies. He is very passionate about integrating subsurface, surface, and finance models to create investable projects. He is also based in the UK. I stop sharing my screen, and floor is yours, Tim Lang.
Thank you very much. I'll see if I can share my screen. Can you see? Can you see the headline?
That's perfect.
Thank you, everybody, for attending this discussion. The title of the talk, if I can just, is there. So we're talking about field development planning, and my understanding is that the exercise that you've been given, or the competition that you're doing, the deliverable, or one of the deliverables, is indeed a geothermal field development plan. So I feel somewhat that I need to give you my understanding of what, at least in the 4 or 5 page summaries that I think you're proposing to write, that what I would like to see if I were one of the evaluators, which I'm not. But this is what I would normally see. I know it's a bit busy, but I want to just talk about some of these things, because if you're familiar with oil field development planning, you'll see it's much more complicated, and the reasons for that I'll try and articulate as we go through. Some of these things I expect you'll find, for those of you who've done this before, are entirely what you expect to see, which is location, infrastructure, etc. The objectives of the project, and the description of the subsurface and the surface development, which, if you're engineers and geologists in the main, then this is not something that would be at all of a surprise to you. I put in there the technology because I think your project is around conventional geothermal systems, whereby you have wells which have matrix permeability between them, and therefore your projects are all about looking at effectively an aquifer water flood. But there are others, EGS, which is the one that we specialize in, and also AGS, which you might have seen in Gerrit Street in Munich. Other things that have been obviously important are the depth, your total vertical depth, and if you're drilling laterals, your measured depths, and the other things you can see before you. What I wanted to do was, and throughout this, I'll emphasize the importance of being completely frank about the uncertainty in your project. Decision makers absolutely do need to know the widest range of interpretation of what it is that you found out. And that's why you'll see me say P90 through P10 metrics everywhere. And I hope some of those things you can see in bullet point 5 are those you're considering entering into your own executive summaries for the competition. I put in there things like Gantt charts. It's important that you've got a robust understanding of the schedule of the project to first energy, or first heat or electricity, and also the phasing of the capex. That's important for when it comes to you engaging with the equity and the debt as to how you can de-risk the project for them, because the more you can de-risk it for the equity and the debt, the lower your the expectation of rates of return will be from their side. The thing that's going to put this project off the rails for you, and indeed for us, is the community engagement and to the extent to which the local population are in support, and if they have concerns, how you address those concerns. And so you may not see so much of this in some oil and gas projects, especially offshore, but I would say that probably half of our time is spent on the engagement and the action plan, and the second thing down, which is establishing customer commitments for both heat and electricity. That's quite different to what you expect to see in an oil and gas project, where normally if it's oil, all you need to do is make sure you have a route to market for your barrels. And if it's gas, it can be more complex. Sometimes you'll go through an integrator or a wholesaler who will then provide the pipeline transportation. But if you compare that with the complexity of a geothermal project, whether that's electricity only or electricity and heat, it is chalk and cheese. And that's the thing that I, as from the oil and gas sector, have found it hardest to understand, is that really the project lives or dies by community engagement and the ability to talk to large customers. If you're lucky, you'll have a grid operator, but generally speaking, our experience of Europe is that most grid operators are almost at capacity in their grids. The other thing is that it's one thing to have production capacity; it's another to be able to sell your gas, your heat, and your electricity in anything like a constant manner. Because unless you're in a very large grid, then you'll see that the supplies are very, very volatile. And some days you'll have very high demands, and others you won't, or other hours you won't. So it can be hour by hour differences in productive capacity, and that then affects the way you design your surface facilities. The other things that I guess of importance in any summary is to make sure that the decision makers know who owns the project. So that can be yourself as a developer, it can be various other actors or your co-investors. And also, in some jurisdictions, you need a license to operate geothermal projects, as in a license to operate. And in that case, there also will be working interest in the license. This won't go ahead without equity and debt, so you do need to report in the full development plan who are the likely equity and debt investors. The other thing to worry about is legals. Unlike oil and gas, where it's usually pretty clear who has the royalty or the rights to those minerals, it's considerably less obvious when it comes to heat. And the issue also of severance of surface rights from subsurface rights is a real headache, because very often you find that somebody owns the surface on which you can then put your drilling equipment and your process schematic and your process for your facilities. But when it comes to drilling into the subsurface, you're engaging with a quite different owner. And that can cause all sorts of problems. Where we are in the northeast, the church owns an awful lot of the land, and engaging with the church is no mean feat. It's several hours, several years of discussions and negotiations. The other things that you'll be familiar with, plannings and other permissions, all onshore projects have those requirements. And perhaps one of the longer documents is the risk register. And that register needs to look at everything from the subsurface right through to indeed the customers. So every single part of that, you need to identify the risks, look at how likely they are to compromise the outcomes of the project, and where those are significant risks, you need to have evaluated what are the mitigations for that risk. Okay, so my next going to talk about this is who is interested, and this is important because the field development plan needs to consider all the actors who are likely to have a stake, and that's obviously you as the developer. The other one that is most significant are the press and NGOs, the public. They are probably those that have the greatest interest, because they're the ones who are most commonly affected by whatever you're going to do. In our case, we try to engage with the local council and align ourselves with them. So we provide, for example, heat almost for free, because it then aligns us with the council who need that heat and allows them to decarbonize their own supplies and their own obligations. Maybe they have buildings, or sometimes they have social housing under their ownership. So aligning yourself with the local council if you possibly can is a major objective. Because if you look at the second half of that list, they are also likely the planning authority. They'll also be in charge of health and safety and environmental emissions, and they'll be in charge of building control. So if you have them on one side, then they will help you make sure that you navigate the other part where they're the regulator rather than the co-owner. Equity and debt, of course, and these projects tend to have quite substantial political significance, especially in Europe, where there aren't so many of them. Like France perhaps, and Germany accepted. So you will find that those of the region are interested, and also central government, and you will anyway going to be get the attention, welcome or otherwise, of the energy regulator and the well regulator to make sure that what you're doing is in keeping with their own legislation. Customers, perhaps the trickiest part of these developments is engaging with customers, whether they're heat or power, or indeed zero carbon, by which I mean some users are motivated because they need to acquire carbon credits or reduce their carbon footprint. The developers, heat and private, I've given you some more technical ones there. The distribution network operator, that's normally what you'd call the grid in most countries. And the transmission grid operator is the very high tension wire, maybe 132 kilovolts, that sort of thing. Surprisingly, the water authority, well, maybe not when you consider it, will be most interested in all your activities. And then when it comes to employment and others and other engagements, you'll find that the employers, university and colleges, and in our case in the United Kingdom, oil and gas workers, where the oil and gas industry, certainly onshore, is wound down completely and offshore is winding down, they're looking for jobs. And you'll find that you'll have a very welcome stock of oil and gas skill sets, which you can deploy and retrain for geothermal work. But the point is that a good field development plan considers all of these, and they're very often in conflict, but you need to make sure they're all there. This is not simply a subsurface surface technical plan that you're looking at. So what really matters in the development plan? Well, I hope I made that point. It's important to integrate the needs of everybody. The plan won't work if you've missed out some really important requirement or objective of one of the groups that I've just described to you before. The other thing is, and I've said this before, is I can't overemphasize the importance of being honest to yourselves about the level of uncertainty you have in every part of the plan. So if you look at the subsurface, for example, what is a realistic understanding of the heat in place, a realistic understanding of the productivity of the wells, not immediately, but also in the medium term, and of the flow of heat to those wells, and that's just the subsurface. And then you've got to look at the uncertainty in the equipment you put in there surviving for the whole field life. For example, lots of the chemistry of various waters, geothermal waters, are very aggressive, and you might not see that aggressiveness to start with, depending on your sampling programs. But again, you need to be sure that if you need to remediate those wells, you're able to do so, and you've put that in your economics as well. And I go through to the surface, and then also the customers. Are they creditworthy? Are they going to sign up for a 15-year power purchase agreement or a 3-year one? And if it's 3 years, then how are you going to persuade the investors to accept that there will be other customers 3 years' time once that's gone? These things are real, because when you start to deal with ordinary public sector industry, and if you have to, the residential community, then they have much shorter time horizons than, say, in an oil and gas project, where typically you'd be saying, well, the oil is a commodity, so we know we can sell it anywhere at any time. And with gas, we'll probably strike an agreement, to provide gas maybe to a power station for 20 years. It's quite different in geothermal. I've said this before, that analysis of risks and mitigations is almost the very first thing that I look at once I've understood the objectives of the plan, because this is where you demonstrate you have a really thorough understanding of how the project's going to evolve over the next few years. And I hope I made the point now, but the complexity is in the customers and the contractual status. That's where you'll find much greater learning than you would do if you're an experienced oil and gas person. So starting with the press, our particular technology we use is next generation EGS, which requires us to produce multiple fractures subsurface. So obviously, as you'd expect, we have a lot of interest from the press, the public, with all sorts of perceptions about hydraulic fracturing, which are incorrect. But that's not the point. They need to be reassured, educated, and the benefits of going ahead with this most certainly spelled out. Much in my view of the negative engagement of press, public, and various groups has been that the objective of the hydraulic fracturing has been to produce hydrocarbons. And our experience certainly is when you say, well, we're actually going to decarbonize whole counties with what we're doing, then they start to take you more seriously. Just to give you an idea, so 4 wells of what we're doing at least is equivalent to about 35,000 diesel car emissions. So you can move the dial with geothermal, and I think you're looking at 50 megawatt electric for your projects from 8 wells. And again, that does move the dial when it comes to carbon emissions. And I would suggest in your field development plans, you just make that quite clear what the benefit is to the community at large. Heat customers, the thing about, I know you're not looking to sell heat, although I might ask you to pause when you put in your field development plans about just how much heat you are not using. So if you've got a typical organic Rankine cycle or steam turbine cycle using a binary cycle using heat from the reservoir, and you generate your 50 megawatts of electric from that, there's probably going to be roughly 15, or maybe if you're lucky, 20% of the thermal heat that you've extracted in your heat exchangers. And are you really going to have a good conscience to let the 75 or 80% that you're not using for power generation then basically go to air or go to water? And that's really what's always troubled me about the standard electricity only projects, is that they are extremely wasteful when it comes to thermal recovery. The other thing is money. It takes a lot of money to build a supply plant. In Eastern Europe, of course, everyone's very familiar with this because this has been done for, well, at least half a century. But it is about 4 million in the UK per kilometre to put a supply pipe from a plant like this into a major network like a city. And it also takes a long time, and it's extremely unpopular, as you'd expect, because you basically completely interfere with the normal day-to-day operation of a community by trying to install heat. The other thing is that, and this is true for electricity, so it's relevant to what you're doing, is that you've absolutely got to find anchor loads who are able to commit to much longer purchases than perhaps most of the other industry, light industry or commerce. And it takes an awful long time to get to full capacity in a heat project. Could be 20, 25 years. And the other thing is, because it's extremely expensive to put heat networks in, actually normally heat network operators can only offer a very low price for the heat and still make their own projects economic. So you have definite price pressures on geothermal heat. And the other thing which applies to electricity soon is the volatility of daily and seasonal demand. And the net result of this is you have to install more capacity to deliver power, and it also accept that the energy sold per annum is considerably less than you might like. So it might be a third or a half, or if you're lucky, 70% of what the capacity could deliver. And that, of course, has effects on your production profile. So when you're doing a production profile, make sure you actually reflect how much energy is delivered every year, rather than what, if you like, is the productive capacity, assuming 365 days and 24 hours per day at the maximum rate, which probably you would do in an oil and gas production profile. And don't forget that you're, in this case, you have a natural competitors, which is natural gas and also air source heat pumps. So a tricky business, but really important, because we won't decarbonize Europe unless we can decarbonize the heat customers. Electricity, in some ways it's simpler, because very often your first port of call is a distribution network operator or a grid operator. But the problem around Europe, you'll find when you try and do this, is that most grids are not designed to take large amounts of input from somewhere they've not done so before. And so most countries that have offshore wind have known this along, that all of a sudden they've got to restructure the grid so that it can take power not from a centralized coal-fired power station, but an offshore wind farm. And certainly in our experience, we find exactly the same thing, where we're looking to embed generation close to cities, and then we say, well, we just got, I don't know, 15 or 20 megawatt electric to put to a customer, and the grid says, well, we don't have any capacity for you. We might have it in 2035, but we don't have it now. So then it forces you to look at private wire, and private wire, again, you've got to build it yourself, and it's about £1 million a kilometre. It's not particularly, doesn't take it very long to build. On the order of a year will do that. But it does mean that you're on your own now, and so if your power generation sets, as rotating machinery tends to be, are around 95% available uptime, then you're going to need certainly backup power generation sets, at least the rotating equipment. But you're probably also going to need backup storage, because if you're going to sell to a customer and they're expecting you to have the lights on all day and all night long, if you suddenly ring up and say, I'm terribly sorry, we're off for a couple of days, what are they going to do about electricity? Either they or you need to find some way of backing up your unavailability. And also you're buying switchgear, etc. customers. So this may seem academic to your rather simple project of saying, well, just make 50 megawatts, but this is the reality of life for a power generator, a geothermal power generator embedded in or near a city. But on the other side, if you go for private wire, then actually what you do is you can charge higher prices than otherwise you would get from the network operator. And why is that? But if you look at the input price to a network operator and what they flog to the customers, you'll see it's very substantially different. And they'll justify that by saying, well, we've got the equipment to maintain and we've got our capital costs to amortize. But the truth is there is a big profit margin between the price of the energy going into a DNO and the price coming out. And therefore, the deal is, well, we'll share that with our customers. And also your customers will be receiving zero carbon electricity. And in most countries, they'll receive carbon credits, which they can be sold in the US, in the European Union at $80 a ton of CO2, 80 euros a ton, excuse me. So there are other deals to be done. So you may well get much higher prices if you supply by private wire to customers. But again, you've got the problem, which is that you're then looking at much lower capacity factors. And also, you'll need a whole new skill set, which is you become a microgrid operator and a system aggregator. So those are certainly not roles that I had any idea about when I was in the oil and gas sector. But all of a sudden, you realize that if you're going to do this, then you have either got a joint venture with or acquire these skills yourselves. So location is key. I mean, normally speaking, if you're going to supply heat as well as electricity, you're going to have to be proximate to the heat. For the reasons you saw before, the cost of these pipes are pretty considerable. The other thing is that the electricity customers and the heat customers don't tend to be in the same place. So even if that's going to be a grid connection or private wire, you'll find that you'll be siting your plant for the heat, and then you'll have to find another way of getting to the electricity. For us, we're drilling deep wells, over 6 kilometers vertical depth in our case, and the drilling engineers tell me that it's really important that we drill vertically as long as we can before we then turn for our horizontal laterals. And that's because it reduces torque and drag on the equipment. You want to be near highways and rail, in other words, in order to manage your logistics. And if you're fracking, which we are, and I know you're not, then just to let you know that the amounts of power you draw from the existing system or generate yourself are very high, maybe 24 megawatt electric. And we're looking at storing around 350,000 cubic meters of water for every injector. And for cooling, so in your case, I think you're probably going to cool with air source, in other words, fans, then if the equivalent cooling for us is about a megaliter per second. So they are very substantial utilities that you have to think about when it comes to putting together your field development plan. In some ways, the utilities are more challenging than the equipment. The equipment's pretty easy, as I'll show you in a minute. But in terms of getting all these inputs to the site, that's where the real challenges are, and having the appropriate logistical capacity to get them there. Of course, you're going to have to buy the land or lease it. And my estimate for you is you probably need about 18 acres or 7.5 hectares. If you're doing something like we are, which is EGS stimulation, or probably only 8 hectares if you're simply doing a drilling, completion, and cogeneration plant. Okay, it's a bit small but this is a facilities design. I'm sorry, that is small. It's a shame that, because well, you might see this better if you can blur it up either after the presentation. But this is a surface facilities design which I did for some plants in the northeast of England. So in essence, this is bringing in 100 kilograms a second through for our binary pair, and then it's putting it at 250 centigrade. 40 bar is the pressure you need to make sure that the water doesn't go into the vapor phase. And then we put it through a steam turbine and a condenser. And then in this case, the binary cycle, but the water from the geothermal well drops about 190 centigrade out of the steam turbine and goes into an organic Rankine cycle turbine as well. So you get 2 bites of the cherry in this case, which has advantages, as you probably know, that the temperature of the geothermal production will reduce with time. And if you have a system where you've got both steam turbines and organic Rankine cycle turbines, you have more flexibility on turn down, so you can carry on operating for longer. In this particular case, we're also providing heat to a heat network about 14 megawatt thermal, which explains the greater complexity of the site. But this gives you an idea here. This is typically what we're doing. The technology is pretty old, really. There's nothing in here. I mean, there are lots of very clever new processes, but in principle, all you're doing is Rankine cycle conversions from heat to power. and in our case, taking a side drawer off to supply a heat network. But that gives you an idea of what it's all about. And even here, look how much we're wasting. We're looking at increasing the temperature of our cooling water by 12 centigrade, and that's a megaliter a second of water. Now that can be used for other purposes, and I would ask you to consider how you can use the waste heat from your power generation cycles. In my case, I think we're looking at agriculture, agro-industry, swimming pools, giving the heat to mine water schemes, anything you can think of, so it doesn't just go to air. A bit more, this might be a bit nearer your normal skill sets. I'm not quite sure with your geophysicist and geologist there, but these are the things that we would normally use to get some understanding of the subsurface. And again, this would be part of the field development plan, more detailed report. You probably find that the board don't want to know this, but it's just so you know that these are the sorts of things that we look at. It's important to look at inversion because each of these different data sets has different parameters, but if you can look at them all together, you get a much higher resolution of your interpretation. The other thing to think about, that's imaging, just to understand the subsurface, and then seismicity records. You do need a baseline for whatever particular form of geothermal you're doing. In essence, you're injecting water and recovering water, unless you're very lucky, like you are in Italy, and therefore there will be seismicity, and you need to allow yourself to check that against what's nature anyway. This is a cheeky calculation because you can argue with it, which is what I wanted really. If you look at this, this is a straightforward saying, well, I've got a cylinder of rock which I'm stimulating. It's 300 meters in radius and 3 kilometers in length, which is pretty typical for an EGS system. So you've got your rock volume there. Now this is the thing that's interesting. So I think probably in our case, the realistic temperature range for production is 265 to 180. You probably could go 180. But the thing is, this 180, when you come to surface, is probably the useful heat. Now, if you look at some estimates of heat in place, you'll find that this number here isn't 80. What isn't the lowest temperature that you can run the cogeneration system at, or the power generation system. You can see people using the re-injection temperature of the water if it's a system like that. That's interesting because that tremendously overstates what the heat in place is, because it's not the useful heat in place. It just happens to be the difference between the temperature of the virgin reservoir and what you're re-injecting through the injecting. So have a think about that. This isn't the right answer, and there isn't a right answer yet. And it's partly an issue that we're looking at within the Department of Energy in the US, which is how do you evolve a common language for reporting things like heat in place, reserves and resources. And there's a big project going on right now, which David alluded to, which is the GEODE project in the States, and I'm leading the Geothermal Resource Management System part of that, which this is part of. So that's why I just gave you that little bit of a background to heat in place. Modeling, yeah, so I'm sure this is completely common to you. In my particular case, we're modeling an injector and then surrounding it by 1, 2, 3, or 4 producers, and indeed other things. And we're looking at several injectors, so we're looking at how far apart they have to be to avoid interference with them, and are there more complex configurations that can help with the recovery factors. These are I imagine some of the things with your 8 wells you'll be looking at, how to optimize the outcomes on the project field life of different ways of developing your injectors and producers. Just so you know, we use a couple of models which are both open source. One is GEODE, which is a pseudo 3D model, which uses pipes to represent 3D hydraulic connectivity. All the references are there. Dr. Luke Frash, he's a nuclear weapons engineer, but he's also has a passion for geothermal on the side. That's why he's at Los Alamos. And for those of you who are at Imperial, you may know Alan Gringarten, who's been a professor until recently for the NSC course. In 1975, he wrote a seminal paper, which has been much not so much hasn't been seen for its great power, but actually what he sat down in 75 the principles for an EGS reservoir development, and the US government picked it up in 2016, and now it's part of an open source model using a plastic domain transform. That's what we're doing, and here's some answers. So I know it's a bit small, but this is a configuration where you've got an injector, in our case, surrounded quite closely by 3 production wells. and you won't in your case be surrounding them so much closely, but the principle of looking at different configurations and looking at the production profiles that they produce, and then in some way estimating the difference in value of those is what you're going to need to be doing. In my particular case, I've looked at changing the separation between those production and injection laterals. I went from 100 to 200 meters. I also looked at changing the flow rates, because of course the higher the flow rate, yes, you advance the the revenue stream, therefore from a net present value perspective that can be superior, but at the same time you could be damaging the reservoir and then it might have to abandon earlier than otherwise. So there is maybe a link there. And the other thing is what happens if you increase, in our case for the EGS reservoir, the number of production wells you surround the injection well by. So as you can see, if you just scan down these, it's most valuable to increase the number of production wells per injector at least to 3. After that, it looks pretty marginal and almost certainly wouldn't pay for the extra production well. So it just gives you an idea that these are the kind of sensitivity analyses or incremental economics analyses that you really ought to be doing in your field development plan in order to show the board and indeed the other actors that you really have got to something close to the optimum, which is still robust, and so that if things go wrong, then you still will have a good project. I think that this is when you're actually drilling the wells. So in our particular case, we're drilling fairly hot, about 270 centigrade. And so the LWD equipment, which is vital because we're directionally drilling, we therefore need to make sure that the equipment doesn't ever see a temperature above 175 centigrade, at least for most of the equipment on the market. That's the electronics fry temperature, after which you've just got a lump of metal that's millions of pounds worth that you've lost. So you do need to keep this equipment as cold as possible so it can continue to operate. Oriented core, very important for us for fracture orientation. I think it probably is for everybody actually. You just do need to know what's going on in terms of the stresses. Stresses are really important when it comes to water floods. I remember some work that was done, I can't remember who did it now, an SB talk I was sharing, where they're looking at, when it comes to water floods, the importance of fracture orientation in terms of the efficiency of sweeping. So having a think about that. For us, we're looking at not the normal things in core analysis. You'll be looking at special core analysis, all the normal parameters you get from like an oil and gas type core analysis. Interesting, just so you know, for us, we're looking at unconfined compressive strength. That tells us how fast we can drill. Young's modulus and Poisson's ratio, that tells us quite a lot about how the horizontal stresses will relate to the overburden, and fracture toughness because we're fracturing. Gyro surveys, very important if you're drilling near other wells, is to establish just whether you think you are where you really are, and because this ellipse of uncertainty at high depths and high lateral lengths can be quite substantial, and so we certainly consider having gyro surveys in all our wells to make sure we understand where we are. And the normal open hole logging suites, calipers, etc., and mini fracs in our case, again, probably not so important for you. Yeah, so what's the right casing selection size? Well, we look at vertical and horizontal separately, and looking at effectively just, this is a spreadsheet type calculation. I've hidden most of the rows, but you need things like Reynolds number and various other parameters to work out what kind of pressure drops you're looking at. I commend you to do this because it rapidly tells you, for our case, we're flowing at between 60 and 100 kilograms a second, or that's the fourth column in, that's the meter cube, so kilograms is 1,000th of that. And as you can see, you need a 9.5/8 on bottom to get a tolerable pressure drop across the well. And I've translated that into shaft horsepower, because ultimately, if you're generating power, then you need to look at the parasitic loads on that power before you export. And the main parasitic loads, other than within the Rankine cycle, are your vertical casing, horizontal casing, and through the reservoir. So making sure those are manageable numbers, and you're not losing, megawatts of electricity just because in your circulation, that's an important parameter, and that's what you need to look at. There is unfortunately another side to this coin. There always is. If you flow at too low a superficial velocity, for example, if you flow a 9.5/8 at say 20 or 30 kilograms a second rather than 60, then the residence time in the pipe goes up substantially, and then you start to lose more heat from the wellbore into the formation. And so it is a balance between maintaining a high superficial velocity of a vertical casing and trying to control the pressure drops. There's got to be something somewhere, but that's it. And if you want to get 100 kilograms a second, which we do, I think probably, then you're looking at something more like a 13 3/8, or at least part of the vertical hull to have 13 3/8. And the lateral's a bit different. The most important thing about the lateral, which we learned, is that our drilling team don't care what we do in terms of completions. They're still going to drill an 8.5-inch hole, whatever else we say, because so far as they're concerned, that's the best hole size to drill laterals with. Our laterals are 10,000 foot long, and they're saying we're not going to tolerate a lower sized drill bit than an 8.5. But for us, once you put the casing in, then there are various options. And the reason there are, because bearing in mind, if you're injecting a lateral, then then the pressure drop across the lateral goes down as water gets injected into the reservoir. So for horizontal wells, it's worth looking at this and optimizing it. The other thing to look at is buoyancy effects. They're pretty substantial. Certainly in our case, we're at 6,500 meters. Then here are pressure drops down we inclined the pipe to try and equalize the pressure across all the perforations in the lateral. Otherwise, what happens is you get preferential movement into the heel of the well, and therefore you get an unstable flood front. And the most important thing in when you're doing geothermal production from laterals is that you stabilize the flood front, so you sweep the whole of the, in our case, 3-kilometer area rather than just the first half of it. Buoyancy, so I think look at the buoyancy here. So the buoyancy here is the difference in pressure and in the water density between 75 centigrade and 260 in our case. And that's a pretty substantial number. It's about 1600 psi, which is way more than any of the pressure drops. And so this is a natural siphon, this reservoir, and that you can take a good consideration on when it comes to designing a surface facilities equipment. Worth a look. This is in fact the well design. This is not the final one, but it gives you an idea. This is our lithology down to 6,500 meters. And it's the hazards actually in the first 1,000 meters, because this is where we've got coals and other kind of things there, and indeed quite a lot of mining activity in this area. And so to avoid having to go down casing sides and then not achieve 9 5/8 on bottom, we've actually put an extra casing string in here, our intermediate string, an 18 5/8. So we're going to put a 24-inch casing in and then put a 22-inch bit into that, and then drill until unless we get some kind of failure, in which case we run the casing and carry on in 13 3/8. So that's the kind of thing that you need to think about. You do need very large IDs on bottom, or else it just completely constrains how much water you can flow. So just a thought to you there. Coming in now, so logistics. In our case, we need super rigs, and there's really nowhere in Europe who has the capability of both the physical equipment and also the teams to drill the kind of 10,000 meter wells in 270 centigrade that we're looking at. So we're going to the States for those. There are stimulation fleets in Europe. And the other thing is that in our case, we're looking for proppant, and actually I mentioned China is probably the best place. And our tubulars come from probably Japan or China, unless there's spare equipment in Aberdeen. But most of the products, of course, will come in our case from Aberdeen in the UK. You do need to think about this, and it needs to be part of the field development plan, because if you're going to order tubulars from Japan, then there are lead time issues that come into play, and those might affect your schedule, and it just needs to be looked at. Long lead items are always important, always good thing to look at to start with. Staffing, again, you need to think about: do you have the skill sets in country to do what you need to do? We don't. So certainly there's no one here who can drill these temperatures, so we need to go to the States for that, or Canada. And for completions, nobody in the UK or indeed Europe can frack a well, so in the ways that we need, sort of these long fractures. But in terms of the rest of it, well, really, that's down to European expertise. Plenty of people, no granite, which is our case. Subsystem modelling is, etc. So everything else is in our case Europe or UK. And have a think about it anyway, because these projects only work because you get experts in from wherever you need them. Capital structure, it's important for us. We're further down the line than your thought experiment in Croatia, but still you need to think about this. That how are you going to bring the equity in? In our case, we need equity to go to FID, and then there's every case that we can split the equity debt so that we can lever the equity and provide the kind of rates of return that you need to, which is in my view, in excess of 15% to the equity, probably more like 20. Paybacks, in our case, we're paying back 6 years after. Where do you get these investors? Well, if you have economic projects, then you can go to the European markets and the USA. Insurances, Munich Re are very good at insurances, so there's no need to go outside Europe for that. I thought there was one other thing. Yes, this seemed to slip this slide. Sorry about that. But yeah, so I know that your next talk is on financial valuation, so I just thought I'd throw in a few ideas as a backdrop to that. So the main thing is make sure you cover the full waterfront of uncertainty with everything you do, and how you then decide to combine those uncertainties. You could do 3 deterministic cases, or if you do 3 deterministic P90s, you're probably looking at a P99 outcome because of the probabilities are independent. But somewhere you've got to be producing economic evaluations that have some sort of a bell curve or some sort of a range among them that is credible, so that your board know where they want to put their risk reward marker. What are they prepared to invest in? Don't forget taxation, and don't forget fiscal incentives or government grants in some cases. In the States, which I know well, then their fiscal incentives are very attractive, and indeed can be made more attractive by using financial instruments. But again, that's those kind of things I'd be expecting you to look at when you produce your final evaluation story to your board. And going backwards rather than forward, that's it from me. And thank you very much for your attention.
Great, thank you very much, Tim. We have one question from Jack regarding if any templates is going to be shared with participants. I just talked to our team, and they said yes. They will share a spreadsheet later on Discord. So if you have any more questions regarding that, please don't hesitate to post it on technical Q&A channel on Discord, and maybe you want to mention Mike as well, so he's responsible for that. He can come back to you and answer those questions. We have one question for you. What sort of rig spec is needed to drill these larger diameter hole sections, especially at depths needed?
We superflex rigs in the States that are drilling the further wells at the moment. So I think £1 million or £1.5 million wells rigs, and probably 6,000 horsepower, 2,000 horsepower, 3 sets of pumps. So, but it's not so much the specs in terms of the size of them. It's also the automation, the AI inputs to the control. So if you look at the main differences between the way I'm not an expert. I'm told they're drilled in Europe and the US is the weights on bit in the US are many fold higher for these granite wells, and there are all sorts of reasons why that's not normally done. And I suppose rather like an aircraft, some of these modern fighter aircraft, they're completely unstable unless you have computers controlling them. The same is true of these drilling operations. They are overcritical. Humans can't really control them, so you need to have full automation as well.
Cool. We have
in regards to heat production profiles, do you consider any production loss through the years, and then I lost the rest of that one,
or unlimited heat supply?
Oh no, I mean the very rare geothermal reservoirs are unlimited. I mean because most rock is not very conductive, and so unless you're blessed, like we were in Italy a couple of months ago, where we were seeing that, where we spoke to the operator, and they said, well, these reservoirs will last probably until the end of time. But the normal reservoirs are nothing like that at all. They're more like oil and gas reservoirs, which is that what you're doing is you're establishing how much heat's there that can be recovered in a reasonable length of time. And then the real question is, what's the optimal way of recovering it? Are you going to recover it very quickly and maybe reduce and get less, but increase the net present value that way? But don't forever think that when you do one of these developments that you assume that you've got heat coming in as fast as it's going out. It's nothing like that. You're taking out heat 10, 20 times faster than it will be recovered. Sure, go back, your grandchildren can go back and have a look at it, but generally speaking, you know, that we're doing projects just like oil and gas projects.
Thank you. And we have one more question. How do you model the heat loss over time?
Well, I mentioned Gringarten in 1975. So if you look at if you read that paper, or if you read Augustine's 2016 paper, which actually applies it in a way that is easy to understand and produces some of the results, then you'll see how you model it. In other words, the simplest way of modeling an EGS reservoir. I mean, if you're modeling an aquifer flood, which I think is what you're doing, then you model it the same way you model an oil and gas reservoir. The only difference is the fluid changes. And in that respect, if you've got a water flood in an oil and gas reservoir, by the time you only got 5% water cut, you know, if you've got 95% water cut, it's the same as modeling. There's no difference in modeling a strained matrix permeability or matrix plus fracture permeability reservoir. Just use all your normal oil and gas tools that you're familiar with. If you're doing an EGS reservoir, then of course you can use those tools as well. But the way you can do it quickly is to use Gringarten's 75 thesis, which has been made user-friendly by Augustine and the National Renewable Energy Laboratory. So take a look at those references I put into the slides.
Lovely. I think
Jack, putting development plans, tools, and templates, which ones will be made available? That's not.
No. That was the first question I addressed. So yeah, we'll share a spreadsheet later on Discord. So
there's one here: reference information on capex and lead times for a heat network. Yeah, well, Jack, yeah, but you know, I've given you a development plan for heat and power. I'm not talking to your project. I'm referring to it, but I'm trying to introduce you to the real complexities of a heat and power project. Yes, Jack, you can simplify the thing and just think about electricity. But I ask you in your full conscience to think about the 75, 80, 85% of heat you're wasting, because your organic Rankine cycle or steam turbine cycle is only using 15 to 20% of that thermal energy. So what are you going to do with the other 80%?
yeah, and Jack responded, thank you. Cool. I think we have no more questions. And thank you very much, Tim, again, for your nice presentation and your time.
My pleasure, David. Good to see you again.
Good to see you. Thank you. Thank you, everyone. We will have one more session tomorrow at the same time, and that would be the last but not the least, of course. See you again tomorrow. Bye-bye.